Welcome back. In our previous lecture, we derived our governing equations for the general three-dimensional case. And now we are going to look specifically at a two-dimensional case where the two dimensions are in the horizontal plane, x and y. This is sometimes called areal flow modeling because we're looking, if you look from above in plan view, you're looking down on area. This would be opposed to a vertical slice or 2D model, which sometimes we use to simulate the flow of water through a dam or a levee. But in this case, we're looking at flow in an aquifer, and we're not going to simulate flow in the vertical direction, just in the x and y direction. So what do the governing equations look like in this case? And we are going to look at two different cases. First of all, a confined aquifer, and then an unconfined aquifer. With a confined aquifer, we have some sort of impervious layer or aquitard above and below the aquifer in question. That doesn't necessarily mean it's completely impervious, but if it is 3 orders of magnitude different or more, then we can consider that to be an aquitard relative to our aquifer. And so the thickness of this in the z direction is b, and we're going to simulate flow in the horizontal or xy directions. So therefore our problem is going to be defined in terms of x and y. So if we go back to our general equation that we derived for, and if we just eliminate the z term, since we're only looking at flow in x and y. And by the way, in a confined aquifer, you do primarily have horizontal flow. If you're near a well, you're going to get some vertical flow, but assuming it's homogeneous, the flow is going to be primarily in the horizontal direction. So it's a pretty safe assumption. So again, if we take our general form of the governing equation, and since the right-hand side is 0, we are neglecting sources and sinks and transient terms for the time being, but those can be easily added the same way we did for the general equation. And so we've simply eliminated the z term. And if kx equals ky, we get this expression here. Kx goes to k and ky goes to k, and we just divide both sides by k. And this bottom equation is sometimes called the Laplace equation. But we have to account for the aquifer thickness. In the more general case, we assumed a unit volume of the aquifer 1 by 1 by 1. Actually, we assumed it was dx, dy, dz, but we could have also, it would have, the derivation, since the dx, dy, dz term, you divide it out and get rid of it, it works equally well assuming a unit volume of the aquifer. So in this case, we're going to do a 1 by 1 by b representative element. So it's 1 in x, 1 in y, and then the thickness is b. And so therefore we multiply each term in the equation by this thickness b, because it represents it has to do with the volume of flow that the water flows through. Through each face, it's through an area of b by 1. So I'm skipping some part. We could go back and rederive this, but suffice it to say that we just multiply each term by the thickness b. And it turns out that the thickness of an aquifer multiplied by the hydraulic conductivity is something that we call transmissivity. And how much water will flow through an aquifer is a function of not just the hydraulic conductivity, but also the thickness. So transmissivity is a really useful and common term. You'll see it quite often in discussions on aquifer characteristics. And so we can also define a transmissivity in both the x and the y directions as shown here. So if we substitute that back into our equation, we have tx times second derivative h with respect to x, ty del squared h del y squared equals 0. So really, that's it for a confined aquifer. We just get rid of the z term and replace kx with tx and ky with ty, and we are ready to go. That's all there is to it. And typically tx is equal to ty, and if we're dealing with a steady state case and there's nothing on the right hand side, we can divide by t, and we end up with basically the Laplace equation again, which you could solve with a simple flow net or with a numerical model. So here are the governing equations for a confined aquifer. If you see that transmissivity term, you know you're dealing with a confined aquifer variation of the governing equation. All right, now let's look at an unconfined aquifer. In this case, we have an impervious layer at the bottom, and then the water table is defined by a height of h. If we use the bottom of the aquifer as our datum, we can express the head as the saturated thickness at any given point. And so the upper boundary is now a free surface, and we have both vertical and horizontal flow. So unlike a confined aquifer, we do get a little more vertical flow in this case. So for example, as that water table curves, there can be a little bit of a vertical element as water flows from one point to the next. Now it's primarily horizontal, and we're going to assume that it's horizontal, but we have to do things a little bit differently now. Also, again, with a confined aquifer, the saturated thickness was constant. Now it varies. Furthermore, the saturated thickness is a function of the head h, which is what we're solving for. So it becomes kind of a nonlinear problem that we need to solve. So how do we tackle this? In order to solve it, we need to use what are called the Dupuy assumptions. And if you look at the hydraulic gradient in the x and the y direction, they're defined as del h del x and del h del y, as we've discussed before. One of the Dupuy assumptions is that the hydraulic gradient is constant along a vertical line. So if you pick any point in the aquifer, as you go from bottom to top, we assume the hydraulic gradient doesn't change. Now, the only way that really happens is if you have horizontal flow. So this is a kind of a roundabout way of saying, even though that free surface is curved, we are going to assume the flow is horizontal, even though it's not entirely horizontal. And the reason we do that is it simplifies our math, and it's mostly horizontal, so it ends up working out to be a reasonable assumption. And this bottom paragraph just describes what I mentioned before. We use the bottom of the aquifer as the datum. The thickness of the saturated region is equal to the total head, which is what we're trying to solve for. And so here's our representative element. The x and the y dimensions we're going to assume are 1. So delta x is 1, delta y is 1. And then in the z dimension, that thickness is h. And so if we look at the flow in the x direction and express that using Darcy's law, we have qx equals minus kx del h del x times a. This is just the basic form of Darcy's law. However, if you look at our element, the area that is flowing through, which is this area right here, the shaded box, that the dimensions of that are h times 1. So go to our next equation here. We replace that area with h times 1, which is basically h. And then likewise, in the y direction, we replace the area with h times 1. And so then, from conservation of mass, again, skipping a little bit here, but based on our prior derivation in the for the three-dimensional case, you could rederive it and get it to this point in terms of the qx and qy, and those have to sum to 0. And so if you plug qx and qy using the modified form of Darcy's law, which we just derived, and plug that into that equation, you get this expression. And you probably don't recall this, but if you think back on calculus, you can show that if you take 1/2 the derivative of h squared, you get h times del h del x. So those you can show based on that derivative that these two things are identical. So if we replace, if we use this assumption, and again, looking up in these terms, we have this h del y and h del x. And using this expression here, we do a substitution, and we get this term here. When we've pulled out the constants from inside the derivative, the 1/2 and the kx and the 1/2 and the ky are constants, we pull them out. And so now this is the solution that we have for the unconfined case. And of course, if there's nothing on the right hand side, we could divide by 1/2, and we get kx times the second derivative of h squared, and ky times the second derivative of h squared with respect to y. If kx is equal to ky, then we have just k in those terms. We can get rid of the k term. But basically, the bottom line here is for the unconfined case, we end up with the same general form of the equation, but instead of having the second derivative with respect to h, we have the second derivative with respect to h squared. So whenever you see this h squared term in a governing equation, you know that you've applied the Dupuy assumptions, and this is for a 2D aerial case for an unconfined aquifer. So in conclusion, for both the confined case and the unconfined case, the equations look very similar. For a confined aquifer, the only difference is you replace K with T, the transmissivity. And for an unconfined aquifer, you replace the H term in the second derivative with H squared. Makes it a little trickier to solve for, but you can solve for that. And so why did we bring this up? We're going to be mainly dealing with the full three-dimensional term, because just in terms of completeness, if we're talking about governing equations for groundwater flow systems, you will sometimes see these forms. And earlier versions of mod flow, based on the layer type in the grid, you would input transmissivity instead of K. But we are going, for this course, we're primarily going to use the three-dimensional terms that we came up with before, but I wanted you to be familiar with these other two special cases as well. Thank you.